Imagine a world where deep learning evolves without the need for backpropagation. Deep learning has transformed many industries, but backpropagation, its core training method, has its drawbacks. It's often computationally intensive and hard to scale in distributed environments. Enter NoProp, a revolutionary gradient-free learning method that could change the game. Drawing inspiration from diffusion models and flow matching, NoProp allows each neural network layer to independently learn by denoising a noisy target representation. Unlike backpropagation, which updates model parameters using gradients, NoProp operates without explicitly calculating or propagating gradients. Instead, each layer in a NoProp network predicts the target label from a noisy version of the label and the input data. This prediction process helps the layer learn to denoise the target representation, bringing it closer to the true label. This gradient-free method offers several key benefits. Firstly, it simplifies the training process and cuts down the computational load tied to gradient calculations. Moreover, NoProp's design supports efficient distributed learning, as each layer can be trained independently without needing to share gradients between nodes. NoProp employs a residual network structure, where each block processes information in a feed-forward manner. Each block, denoted as, takes two inputs, the previous layer's latent state and the original input data. Within each block, a neural network maps these inputs to a new latent state. The final latent variable is then passed through a linear layer followed by a softmax function to produce the predicted label. A key component of NoProp's architecture is the use of class embeddings. These embeddings represent each target class in a high-dimensional space. NoProp offers flexibility in how these embeddings are incorporated. One option is to utilize fixed one-hot vectors, providing a straightforward representation of each class. Alternatively, NoProp allows for learned embeddings, which are jointly trained with the model parameters. Learned embeddings provide an interesting opportunity to gain insights into the model's understanding of the data. When the dimensionality of these embeddings matches the input data's dimensionality, they can be interpreted as image prototypes. These prototypes represent the model's internal representation of each class, potentially revealing valuable information about the learned features. Imagine a world where training neural networks is as seamless as a walk in the park. With NoProp, this vision is becoming a reality. Each diffusion dynamic block in a NoProp model is trained independently, focusing on denoising its target representation without relying on gradients from other layers. This innovative approach ensures that every block works autonomously, making the training process more efficient and robust. To keep the embeddings from collapsing into a single point, the linear layer and the embedding matrix are trained together. This joint training ensures that the embeddings remain rich and informative, effectively representing the diverse target classes. Researchers put NoProp to the test on several benchmark datasets, including the well-known MNIST, SciFAR 10, and SciFAR 100. The discrete time variant, NoProp DT, delivered stellar results, matching or even surpassing traditional backpropagation methods in accuracy. Moreover, NoProp DT outshined other gradient-free learning techniques, such as forward-forward, difference target propagation, and local greedy forward gradient. Beyond just accuracy, NoProp DT showcased remarkable memory efficiency compared to backpropagation. This efficiency is due to the elimination of the need to store gradients during training, a major contributor to memory consumption in traditional methods. With its reduced memory footprint, NoProp DT is perfect for resource-constrained environments or handling large-scale datasets, making it a game-changer in the field. NoProp's emergence as a gradient-free learning method challenges conventional wisdom in deep learning. The ability to achieve competitive performance without relying on backpropagation raises fundamental questions about the necessity of representation learning in its traditional sense. NoProp's success suggests that explicitly learning hierarchical representations through gradient descent might not be the only path to achieving strong performance in deep learning. The development of NoProp opens up exciting avenues for future research. Exploring its applicability to other domains beyond image classification, such as natural language processing and reinforcement learning, could reveal further insights into its capabilities and limitations. Additionally, investigating the theoretical foundations of NoProp's effectiveness in learning and generalization could provide a deeper understanding of its inner workings. In conclusion, NoProp represents a significant leap forward in gradient-free learning. Its novel approach of denoising target representations through independent layer-wise predictions challenges existing paradigms in deep learning. The competitive performance, memory efficiency, and potential for efficient distributed learning make NoProp a promising direction for future research and development. As the field continues to explore alternative learning algorithms, NoProp stands out as a compelling example of the innovation and progress driving the evolution of deep learning.